Greetings, the thesis chairmen and the committees. So our projects focus on the strengthening of two-way flat slab against punching shear using post installations of GFRP rods. สวัสดีครับ My name is RTJ-Strengthening. I'm here with Titi Amnowong and Rashanon Dishaim. Today's presentations contain 4 parts, which are the introduction, theory review, discussions, and conclusion. And now Rashanon Dishaim is going to take the stage.
Moving next to our introductions. Nowadays, people have been using flat slab, do away with the series of advantage by eliminating the beams. Concrete formwork and scaffolding are simplified. These make the construction process become faster, easier, and less expensive. But with the characteristic of the flat slab that directly supported by the column, make it more vulnerable to bonding shear failure compared to other conventional slab. Bonding shear failure in flat slab will occur when shear stress are more than our equal shear capacity. This will make the slab penetrate through the column as shown in this figure here. So to prevent this from happening, we need to strengthen the slab against the bonding shear failure. In this slide, show all the methods that can be used to strengthen the slab, which consists of drop panel, column capitalized, and post installations. But in this case, we select post installations because it benefits that the original geometry can be maintained, the intervention remain invisible, and also the size and weight are not increased. Moving next to our objective, first is to study the behavior of bonding shear failure. Next is to study the effect of at least 3 strengthening patterns, which consists of cruciform, double line, and radial. In this slide, it's shown the specimen dimensions, and on the right figure, it shows the layout of our specimen. Moving next to our test setup, on the right figure here, our test setup was simulated to be the same as the actual bonding shear failure that occurred in the real constructions by applying the force on the hydraulic jack upward into the point of the column. In this slide, show the apparatus that we used in our test setup, and the specimen will be holding into the test setup by using the anchorage system. Moving next to our specimen details, which will be classified into 3 different patterns, which is cruciform, double line, and radial. And each pattern will be divided through different of number of wave lines, with each 4 and 7. As shown in this figure here, next part will be the theory review part, and Titi Anavong will be the one who lecture it.
Let's move into theory part. Shear strength is referred to design code ACIT18 version 2014. Flat slab without shear reinforcement, its shear strength is only provided by concrete. There are 3 equations for calculate and is governed by minimum equation. With shear reinforcement and failure within shear reinforcement section, the shear strength is provided by concrete and shear reinforcement. The limit be imposed on the cumulative strength in order to avoid concrete crushing. If in case of failure without shear reinforcement section, shear strength is provided only concrete, and critical section will spread out shear reinforcement zone equal to a half of effective depth. For calculation flexural capacity of isotopic two-way flat slab, Johansen-Uline theory is introduced. Next topic is result and discussion.
Let's start with how each sample failed. Take a look at the final crack of SP0 at the ultimate load. You can see a little square-like crack form in the middle of the specimen. Such crack continues all the way to the bottom of the specimen, it forming a cone-like shape. Such cone, we call it punching shear cone. With the punching shear cone and the strain in rebar, it suggests that SP0 fell under punching shear. If we were to map the sample out, you can see the cone more clearly. Now for the SP1 and SP2. SP1 and SP2 exhibit a completely different crack from SP0. Sorry, SP1 and SP2 cracks look like a line running through the middle span of the sample, making it look like the sample fall. Strain inside the rebar suggests that SP1 and SP2 fell under flexural mode. Not only the crack pattern that SP1 and SP2 share, they both share a similar load, similar ultimate load. But however, SP2 exhibit 25% more in terms of defections at the ultimate load. It means that SP2 bend 25% more at the ultimate load than that SP1. When we plot all the specimen load and deflection side by side, you'll see that the curves are more likely the same. They can be categorized into 3 parts: the incremental part, the the turning point or the ultimate load and the decremental part. For the first part, the incremental point, all specimens seem to exhibit a linear trend, which we call the elastic trend of the curve. But after it reaches the ultimate load, the decremental seems to be depending on how the sample fell or which limit state is the one that govern. For example, SP0 shows a sudden drop in load, and it fell under punching shear. This means that SP1 and SP2 fell under a different type of failure mode, which is the flexural mode. You can see that the decremental part of SP1 and SP2 seems to be a lot more gradually compared to SP0. Take a look at the summary of the ultimate load of all the tested specimens. With SP0 where there is no shear reinforcement at all, SP1 where there is a certain amount of GFRP strengthened, and SP2 where there is even more amount of GFRP. You can see that SP1 exhibit a higher ultimate load of SP0 since there is a shear reinforcement inside. But however, SP2 has a similar amount of ultimate loads to SP1. It shouldn't happen that way, but it happened that way because the punching shear capacity has surpassed the flexural capacity, which caused the flexural failure to govern the SP1 and SP2 specimen. This means that strengthening by GFRP can increase the amount of punching shear capacity. Not only the punching shear capacity that strengthening by GFRP provides, but it also increases the amount of ductility of the specimen too. The ductility is defined as the relative deflections at 20% drop of ultimate load on the decremental part only to the relative deflections at U point. So we calculated the ductility gain from post-installing GFRP into this simple table. First, SP1 exhibit around 14% increase in ductility with around 2.4 meters of GFRP embedded. But for SP4, where there is twice the amount of GFRP, it increased the ductility of the sample to 26%, which is a significant amount of ductility that we are talking about. So when we come to the load contribution of GFRP, it can be determined into three simple steps. Find the Young modulus by tensile strength test of GFRP. Then we monitor the strain of GFRP during the test. Then we do some back calculations. We get that SP1 takes around 8 kilonewtons of load and SP2 takes around 36 kilonewtons of load, which is about 4 tons. Now to sum things up, let's change the complex figure name into something even more simple. So SP2 is going to be nothing since there is no reinforcement. SP1 is going to be some GFRP and SP2 is going to be lots of GFRP. In terms of limit state, all the flexural capacity of all the specimens are equal, but however the punching shear are different. For example, SP0 where there is no shear reinforcement at all, the punching shear capacity was governed since it was lower than the flexural. But when we put some GFRP inside, the punching shear capacity increased and it surpassed the flexural reinforcement, that we get the ultimate load of SP1 to be around 1.15 and SP2 too. The punching shear capacity of SP2 also surpassed the SP1, but however it fell at the similar load since flexural capacity was governed. That's why we get the same a similar amount of ultimate load. Now when it comes to ductility, when a specimen is strengthened by the GFRP, it also removes the brittle part of the specimen, which is the concrete, and replace it by something even more ductile when we compare to concrete, which is the GFRP. The ductility gains are on the screen right now.
This project can be concluded that our slab were strengthened by using GFRP loss. The shear strength is improved and adequate to prevent punching shear failure. It means that the failure mode shift from punching to fracture. In case of ductility performance, slab SP2 gained the highest ductility with approximately 26%, followed by 14% in SP1 when compared to control specimen. Therefore, double line pattern is discovered as the best strengthening pattern. This part shall predict the result of untested slab. Table 4 show the theoretical load capacity of untested specimen, which are the shear capacity and fractional capacity. According to the result of tested slab, they fell under fractional failure because all of slab in this project were designed to govern by fracture. The GFRP lot proved that it can enhance shear capacity until over fractional limit state. Thus, SPT to SP6 shall fail under fracture also. Furthermore, among of the whole of them have more than SP1 and SP2. Due to closer spacing of shear reinforcement, it means that net area of concrete is decreased. SP1 and SP2 exhibit first crack at location of shear reinforcement with 80 kN at the beginning. For this reason, SPT to SP6 prone to reach the first crack before 80 kN, but it may greater in ductility because closer spacing of shear reinforcement may effectively contribute to the load.
I would like to wrap up now. So today we have talked about the introductions, the theory review, the discussions and conclusions. Thank you for your attention.